Welcome to the presentation on Lagrange interpolation. So far we had the discussion on polynomial equation fittings. Lagrange interpolation is also one form of polynomial form. It is more powerful than the previous discussed polynomial representation. The given data may not have the equal intervals, it may have the arbitrary spacing values. To solve the polynomial coefficients, it is required to develop the many simultaneous equations. In Lagrange interpolation, it is not required, and directly the final equation can be developed at the end. That's why it is more complex in nature, looks very difficult and lengthy due to shortcut methods. A computer program will solve this issue. Let us consider the quadratic equation, that is the second degree equations. Y is equal to a0 plus a1 x plus a2 x square. In Lagrange form, instead of y is equal to a0 plus a1 x plus a2 x square, it is possible to express the y is a function of x. This representation in the Lagrange form as follows: y is equal to c1 into x minus x2 into x minus x3 plus c2 into x minus x1 into x minus x3 plus c3 into x minus x1 into x minus x3. There are three coefficients, that is c1, c2 and c3, and 3 points are given. Those are x1, y1, x2, y2 and x3, y3. So by substituting these 3 points in this Lagrange interpolation equation, it's possible to solve the coefficients of c1, c2 and c3. By substituting the c1, c2, c3, directly we can get the equation, that is y is a function of x. In the first step of this equation solutions, let us substitute this x1 and y1 in y. So the y is equal to c1 into x minus x2 into x1 minus x3. Whereas in the c2 coefficient and c3 coefficients, the x1 minus x1 becomes 0, and for the c3 coefficients also x1 minus x1 multiplications leads to 0, so that the c1 coefficient directly we can get as y1 by x1 minus x2 into x1 minus x3. Similarly, by substituting this x2, y2 in the equation of y, we will get y2 is equal to c2 into x2 minus x1 into x2 minus x3. As in the first term, that is c1, x2 minus x2 becomes 0, and for the c3 coefficient, x2 minus x2 becomes 0. We will get the coefficient expression for coefficient, that is c2 is equal to y2 by x2 minus x1 into x2 minus x3. And finally, by substituting x3, y3 in equation y, y3 is equal to c3 into x3 minus x1 into x3 minus x2, as the coefficient for coefficient c1, x3 minus x3 becomes 0, by coefficient c2, again x3 minus x3 becomes 0. So that c3 is equal y3 by x3 minus x1 into x3 minus x2. Substituting these 3 coefficients, that is c1, c2, c3, we got the expression for y as a function of x. What we need to substitute, we have to substitute the 3 points, that is x1, y1, x2, y2 and x3, y3 in the final equation, so that for a given value of x, directly we can get the answer, that is y. Let us discuss one example in the Lagrange interpolation solutions. And in the generalized form, y can be written as the product and as well as the sum. The sigma shows the sum I is equal to 1 to n, whereas the product it is showing j is equal to 1 to n. In the numerator it is x minus xa except x minus xi, because x minus xi once I is equal to j is becomes 0. Similarly, in the denominator xi minus xa except xi minus xi, If I is j is equal to I, then this becomes 0. And coming to this example of this Lagrange interpolation method, to solve the properties, thermodynamic properties, for example, the following data is given to find the steam pressure versus steam temperature. For compute the pressure at a given temperature of 375 Kelvin in both the Lagrange interpolation method and MATLAB curve fitting method, and also find the percentage difference in the pressure. The given data is temperature, the 5 temperatures are given, and the pressure is a function of temperature, that is also given. We will use the fitting, the y is equal to the function of x, the numerator as well as the denominator. The pressure is developed for numerator as well as denominator. Finally, by substituting this given data, that is the temperature, we will get the pressure.